All right, greetings everyone. It is October 10th, 10/10/23, and we're in our discussion of chapter 7. So last week, Ali and I recorded like the short video overviews of chapters 9 and 10, just because there was only a few of us during our cohort 4 slot, and we just wanted to complete those overviews. So now we're in the chapter 7 discussion. So we'll jump over to the chapter 7 page. And before we look at like any of the specific questions, like, does anybody just want to share what did they think about chapter 7? What was their impression, or how would they summarize it to somebody, or what was just exciting to them about chapter 7?
Well, can I start? So, Chris, hello, Daniel, hi.
Yeah, go for it.
So,
Go for it.
yeah. So my impression of chapter 7 is about it's mainly about the discrete state and discrete outcome model of the active inference. And I found it is particularly useful to have a detailed understanding of one of the example, which is this T-maze example. And it is kind of the first active inference model that I can get my hand on and try it out and change those parameters or the matrices used in the active inference model, and see how the active inference actually works.
Awesome. I think that's kind of the point. Anyone else want to give a thought on 7?
Yeah, I would just second everything that Wanshan said just now. I think it's a great way to actually see maybe how some of the ideas that we've been reading about prior in the textbook actually start to hang together and play out in an example. I think that the use of discrete variables is highly like kind of interpretable. I think this is it comes a little bit more naturally to me to read this chapter versus chapter 8 with continuous variables, just because we get to see like your more precise specific things that happen, discrete choices and things that occur, and then also just some kind of interesting observations that come out of that with the different kind of components of the model. Like as you get further in the chapter, there's a discussion of like, here are the interesting things that happen whenever you don't include preferences or have highly uniform preferences. Like there's just pure novelty seeking on the part of the agent, who like in the T-maze example, they just can't sit still. They never come back to the same spot. It's pure just seeking epistemic value, it seems, because there's nothing pragmatic to do, because there's nothing in particular that they're going for, because it's not been hard coded into the initialized preferences. So yeah, just giving us that really big model for active inference here in the discrete form, in addition seeing the interesting dynamics that can kind of play out emergent properties and so on.
Awesome. Anyone else want to make a general comment on 7?
I would just echo that, given that I've come from a psychology background, and so seeing the exploitation paradigm just being laid out in that way, and they make a comment that they believe they've come to understand how these two go hand in hand instead of being competitive. I thought that was also very, very intuitive.
Cool. Yes. Yeah, the continuous time setting is kind of like having your hand on the rudder in a boat. And so you're making continuous actions and there's a continuous flow in these paths. And the discrete time is like chess or checkers. Like time clicks discretely and the actions are discrete, the states are discrete. And so that can make it kind of clearer, a little bit more cut and dry. Cool. Does anybody want to jump to a specific section of 7, or we can look at the questions and just like look at the upvoted ones, or if anybody submitted any and just like look at what's interesting in 7, or somebody can propose a section that they want to look at.
I'm mostly interested in chapter 7.3, decision making and planning as a reference. I wonder if if someone else has preference to talk about the
Sure. Well, let's get to
7.1.
yeah, let's get to 7.3. Basically, 7.1 is just one paragraph. We can see here. 7.2 is just a passive inference model. This is just the downstairs section of the discrete time model. We have hidden states changing through time, being related to observations at each time point and a prior. So it's just the downstairs of figure 4.3, and it's kind of worked out in multiple stages with this music listening example. So then we get to 7.3. Now we take that downstairs, the part that looks like an E, and we add in the action. So this is where we actually get active inference. And then what makes it active inference under the free energy principle is that the unified imperative for action selection is going to be expected free energy. So because there are other models that have sense making or signal processing on the inbound, and then decision making or action selection or control theory on the outbound. Like that is, in a loose sense, active inference. But when we're talking about active inference, we're talking about active inference and the free energy principle, which is what we get when we bring in the variational and the expected free energy. Okay, so what aspect of 7.3 do you want to explore?
Well, first about this figure that you're showing here, I have a question about the 4th line from the bottom. Do you see third while C and E appear in the panel on the right? Do you see that sentence? Where is the E? I couldn't find the E.
Yes. So E is the habit. E represents the prior distribution on policies. So let's just say that we have 4 affordances, up, down, left, right. The E vector is like 0.25, 0.25, 0.25, 0.25. So in that situation, E conveys through its inclusion which actions are possible. And by the value in E, that is the prior on policy. So if they were all 0.25s and there was 4 affordances, then that would be like saying those options, in the absence of being sharpened by expected free energy, are equally likely to be taken. And we can look at the nervous system diagram in figure 5.4. So here's E. So here On the indirect pathway, observations are coming in, habits are being triggered. On the direct pathway, we have expected free energy sharpening our habit distribution. That doesn't
I
just
see.
mean, yeah, it doesn't just mean exaggerating it. It could upweight something. Like, let's just say there's a rare policy, but in a given situation, it has high epistemic and or pragmatic value. Well, then you'd hope that even though your prior on doing it is very low, like what's the prior on taking off your seatbelt? Well, on a 10-hour
Right.
car ride, it's low. But then when the car is stopped and you want to leave, that's an amazingly salient thing to do. So E basically hosts what can be done, and in the absence of any decision-making process, the distribution of actions to be taken, and then G sharpens that to update the policy posterior. And then the policy posterior is where action is sampled from.
I see. I see. From the figure 7.3, it seems that C and E plays the same role as affecting the distribution of policy, right? They kind of
Absolutely.
similar role.
Absolutely. Like free energy, expected free energy here, G, can be understood as a statistical distribution about policy conditioned upon C and E. We just discussed why E matters for the calculation of policy posterior. C matters because of equation 2.6. So C matters for G calculation because C is going to decide what is of pragmatic value. So in that representation that they have in 7.3, they're basically just saying policy is being computed conditioned upon preference and on habit.
Okay, so C is preference, E is habit. So they encode different kind of preferences of the policies.
Yeah.
Okay, thank you, Daniel. That's very good.
Cool. Yeah, I mean, anyone else have like a thought on 7.3 or a question on 7.3 or just how they see it or how they interpret it?
So I have a further question. So again, on this figure 7.3, so we see the policy pi affects the probability state probability transition matrix B. I wonder if it's possible to model the policy also affect the matrix A, meaning that it not only affects the probability transition matrix, but also affects the transformation from the state to the outcome.
Great question. I'll kind of mention two ways that you could think about that. So as you mentioned, policy intervenes in B, how things change through time. Like when you turn on the air conditioner, it doesn't like reach into the room and just like modify the thermometer. It modifies how the temperature changes through time. So it modifies the dynamics of the hidden state, the temperature, and then that results in a thermometer changing. So first answer to the question is, we don't need policy to change A. If we prefer it to be cooler and we take the policy to turn on the air conditioner, then in the next time step, the temperature of the room is going to drop. Let's say one policy is, turn on the air conditioner, temperature drops by 1. Turn off it, it goes up by 1. So you turn it on, the temperature drops in the room, and then the thermometer is cooler. So one answer is you don't really want to touch A because the mapping between hidden states and observations isn't really something you can act on directly. And so we're intervening in the real underlying hidden causal process. And then that emits observations first. And the second answer is you could develop an active inference model where a metacognitive agent selects which A matrix to use. So maybe you decide whether to put on sunglasses or not. And then when you have sunglasses on, colors are mapped to your vision this way. And when you do something different, they're mapped a different way. So that would be taking a policy choice on which A to use.
Okay.
But in most settings, the relationship between hidden states and observations is it's orthogonal to, or you could say it's factorized away from how hidden states change through time. Keeping this model sparse in the sense that keeping as few edges as possible keeps the computational cost low and keeps the kind of parsimony high.
I see. Thanks. That's very good. So yeah, so it really depends on how the states and the outcomes are defined. Maybe in my case, we can define it in such a way that the policy affects only the state's transition probability, not affecting the translation from the state to outcomes.
Yeah, in almost all cases, you will have policy only intervening in B. So making a generative model, I mean, this chapter 6, making a generative model is, if you can describe what all of these are in your system of interest, you literally have the generative model. And how do you categorize different things that you have or want to include into this? Well, observations are literally the data. If it's in a spreadsheet, it's literally an observation. Then policies are actions. So if something is something that an agent can do, and then everything else is a hidden state. Now, if you're in a fully observable situation, like a chessboard, then it can seem like there's a redundancy. Like the observation is the location of the piece, and the hidden state is the true location of the piece. So in that case, it's not really a partially observable Markov decision process, POMDP. It's just an MDP because it's a fully observable decision process. But A allows us to bring in the partial observability. But if you're in a fully observable setting, then you can almost think about direct intervention. However, even in that case, then the A matrix is just an identity matrix. Like it maps perfectly between hidden states. You know, you have an accurate thermometer. 37 just maps to 37. Then A is an identity matrix, and it has basically no computational cost. And then your model is more flexible in case you ever did have a noisy thermometer or a missing measurement. If you had a POMDP, then it's fine. But if you were to only have the MDP, then you can't deal with the noisy or a partially observable setting.
Yes, thank you, Daniel. That's very detailed explanation. Yeah, I'll hold my questions for other participants to ask.
Yeah. Anyone want to just give a thought or a question on this section?
Yeah, I guess just since it's been a bit since I actually read, like really did a deep dive on this particular chapter. But I'm trying to make sure I grasp, like whenever they're describing the T maze shortly after, yeah, I guess we're still in 7.3. They just start to describe like the A matrices as, like in this case, they become tensors. Like with the T maze, you have there are outcomes, and then there are locations, and then there are contexts. So I guess the mouse searching for a reward is looking for, I guess the outcome is like whether the space they land on is a reward or not, and the location is just them navigating the maze itself and the locations of the maze, and then also you have the context. I might be mixing those up a bit, but it's just trying to make sure I can grasp, like we're looking at potentially 3D, 4D, and so on, like kind of tensor quantities here that are based on all of the kind of dimensions to what the mouse is doing, rather than just looking at it as like a 2D thing, as nice and simple as that would be.
Yes. Basically, yes. So I mean, you could think of it as okay, well, pull back. The context is whether you're in world state A or world state B. So the two contexts are whether the food is on the left or the right. In this setting, you did mention that. Okay, so now A maps between observations and hidden states. There's going to be two types of hidden states, and so each of them projects out to a given observation. A1 is about location. A2 is about context. I don't know if you would properly call this a tensor, but certainly this is two matrices. But it's not, but they're different shapes. This is a 5x5 matrix, and this is a 3x4 matrix. When we get to B, it will be a true tensor, in the sense that every slice of B is going to be a matrix with the same dimensionality. But here, it's kind of like two parallel channels. Like this would be analogous to having two sensory modalities. So if we had vision and hearing, those A matrices could map to the same hidden state. Like maybe, is there lightning? Or is there a thunderstorm? And you might have a mapping between hearing and is there a thunderstorm, and vision and is there a thunderstorm? Or you can have those two observation modalities map to two different hidden state modalities, like in this case. I just want to make one more point before we continue forward in the T maze, because it was brought up about the explore exploit. The most probable policies are those that lead to the lowest expected free energy. Again, this is one of the key distinguishing features, if not the key distinguishing feature, between active inference, guided policy selection, and reinforcement learning or reward maximization. There is no proposal of a reward or utility function that gets optimized. There's just the definition of the generative model, and then the generative model does the likeliest thing given its setup. Again, that doesn't mean the animal lives. It doesn't mean that XYZ. It just means that given how the generative model is set up, it does the likeliest thing. And then given empirical data, chapter 9, we set up or parameterize the generative model to be the likeliest one. So
Daniel, can I?
Yeah, go ahead.
Sorry. Yeah, I do have a question regarding 7.4, where you're right there.
Yeah.
Here. So I I'm a bit confused what P and Q means. Do we always use P represents the prior or the true distribution and Q as a approximate distribution? Q is this Q the one we actually want the decision that we intend to change our belief by updating our approximation to the real probability. So P is the real
Almost.
probability.
Exactly.
Q is approximate.
Q is the real mapping in this case. So it's a natural log. So this is kind of like taking a surprisal.
Okay.
It's of observations conditioned upon preferences. So this is really what you observe in relationship to what you prefer. And the reason why it has the P is because we're talking about like the actual observations coming in. And Q is the variational distribution that we control.
Okay.
Yeah.
Now it's clear. So
yeah.
actually we can change Q to minimize this GQ, G pi, this object function here, right?
Yeah. Yeah. Like Q are about our beliefs, whereas we don't really get to control in the same way that like Q of observations conditioned upon policy. So what do I believe the sequence of future observations will be, O tilde, conditioned upon what I do? That's all in the mind. That is different than what is the sequence of observations given my preferences. You can change your preferences, but that doesn't change observations given your preferences. And similarly, you could change your belief about hidden states, but you can't in the same way control the mapping between observations and hidden states in actuality. Yeah, and this is like a restatement in equation 7.4 of equation 2.6, expected free energy. So we have same epistemic and pragmatic value. Okay, so let's go through the T-maze and just see how this is going to play out. Okay, so the two factors. So factor is being used to describe a different kind of hidden state. So again, there's two factors here. There's the context factor and the location factor. One of those is a controllable factor, location, whereas context is not a controllable factor. If it were, there would be another policy type, change the food to the left, to the right. But we're not in that setting. So this example brings up the distinction between controllable and uncontrollable factors. So observations, they're the fundamental observables that's in the spreadsheet. Then everything that's not an observation is a hidden state factor. And then some state factors are controllable. Those are the ones that have policies intervening in their B matrices. Other state factors are uncontrollable. It's just a latent cause of the world that's proposed within a cognitive model. But with respect to that uncontrollable state factor, that's like listening to music. The first example, that's like a passive inference on that state factor. Okay.
So the controllable state are the locations of the mouse, right?
Right, because it can move.
Uncontrollable states are the locations of the stimulus.
Yeah, because the mouse doesn't get to decide where the food is.
Right.
Yeah.
Okay.
Yeah. So and that's where agency and self-efficacy can come into play, is to what extent do actions bear upon can the agent take actions and make a difference that makes a difference take an action that changes some state in the world, controllable factor, and then this is all about how they evaluate that. It could be chosen because it has high pragmatic value, because exerting that kind of control brings observations closer to alignment with preferences, pragmatic value, or it might lead to new information about the world, epistemic value. And that's the entropy, the expected difference of the entropies of observations conditioned upon hidden states in comparison with observations conditioned upon policy. So this is basically like the entropy of the A matrix. So that's the mapping between observations and hidden states. Here, we're asking, how much is it going to matter differently if we condition upon policy? So let's just say that the A matrix has a given entropy. The A matrix has a given uncertainty associated with it. The least uncertain A matrix is like the identity matrix, just one on the diagonal and all zeros elsewhere. You have perfect knowledge. It becomes a fully observable setting. The most entropy A matrix is just all uniform. Basically, the measurements don't even matter because all the measurements are equally likely to map to any hidden state. So that's on the left side. And now the question is, conditioned upon action, is there going to be a difference in the sharpness of that mapping? Well, if it's a policy that doesn't lead to sharpening of the A, it doesn't have epistemic value. In comparison, if there's a policy such that you believe that taking that policy is going to sharpen your understanding of outcomes, then this is a non-zero value. So that's the epistemic value.
Yes, Daniel. However, you said that from the model, the A matrix is fixed, right? It's not affected by all the entries in A matrix are not affected by the policy pi, because policy pi affects only the state transition probability matrix B. And what do you mean by sharpening A using policy pi?
Good question. So there's a few pieces here. First off, there's A matrix learning. That is not happening in this example. So but it is a cognitive phenomena that the A matrix could be updated, but it's not being, there's no learning here. Now let's just say that there's we have observations and hidden states. One of the observations doesn't lead to gaining information about hidden states. Like it maps 50% of the time to A or B. Another observation gives you a lot of information about the world. Then that policy the policy that leads you to get that the informative observation, that has a high epistemic value. Now, that doesn't mean that policy reaches into A in the factorization of the Bayes graph.
Right.
So it's not like every single thing. It's like saying, well, how could what the finger does influence the knee? They're not connected directly. It's like, well, yeah, but the whole generative model is executed as a whole. So, you can, I mean, to put it a different way, you can use expressions in the active inference ontology that associate different variables that aren't necessarily connected through an edge here. So these edges are not the only possible sentences that you can construct when talking about the generative model. So you can talk about how G is related to O, right? Obviously. because observations are what are O tilde are what are being taken into account when we're
Right.
talking about G, but there's no line between G and observations.
Mhm.
So this is just asking, will those observations be informative? And
Mm.
so, and the observations being informative doesn't need to entail updating of the A matrix.
I see. I see. Yeah, good point. Good
Yeah.
point.
Or, you know,
Yeah.
there's two people you can ask. One of them, he flips a coin. The other one
Right.
tells you the truth. So the epistemic
Mhm.
value with going to the person who gives you the good information is high, even if you have a fixed understanding of that situation. But
Okay.
let's look at it in the team A's setting.
Yeah. Yeah.
Okay. Okay. So technically, okay, technically the A matrices are tensors,
Mhm.
but it's a little bit of an irregular one. Okay. So here we have these two kind of parallel A's on the first and the second context of A, or first and the second factors, mapping the actual location. Here on the rows, note that there's this L and the R. This is
Mhm.
because the hidden states are, in the cases of being on the right, being on the left, and being in the starting position, those are all identity mappings. But now, because we're in the black on the right setting, the epistemic cue at the bottom, when you are physically in the bottom, you go to the hidden state, which tells you you're in the R context. And there's all zeros here. That hidden state cannot be reached. But of course, when the context is switched, it's the exact opposite. There's a 1 here. Going to the bottom maps you to it's the L state, and there is no way to reach the R state.
Mhm.
And we also see a flipping of the 98s. 98 is here on the bottom left and on the right. And here it's on the top left on the right. This is, again, just to show these matrices are necessary and sufficient for specifying the situation. They
Mhm.
describe literally exactly what is happening. All that your generative model knows is what you specify in these matrices. There's no other information. So that's the A matrix. This is showing the two contexts, and it's showing the mappings between location and this kind of like location plus distinction between the messages that the epistemic cue on the bottom could provide. And then also notice that when you're in the starting or the bottom position, you're in the sort of like dashed line, like you're not finding out anything. But then when you're in, but then there's a 98% chance you have a 98% sensory accuracy. There still is a 2% mapping between if you're on the left in this context and it's black, there's still a 2% chance it maps to white. Okay. Now we get to B. So similarly, we're going to have two B matrices, or two B tensors for each of these state factors. B2, they're going to introduce first, because B2, the context, stays constant over time and can be represented as an identity matrix. So basically, this is just keeping the same thing through time within a trial. And this is where we get the true B tensor. Here, this describes location changes as a function of movement selection.
Mm,
So we have from and to, and then there's 4 actions.
mm,
B does all the work. Let's look at the
right.
generative model. Like, observations are just data points. Hidden states are hidden states. They're just descriptors, proposed or actual latent descriptors. And then this is just a
Mm,
sensory mapping. But all the work of the meaning of embedded action is going to play out through B. The
right.
dimensionality of B is also higher, because B is whatever the dimensionality is of the state factor,
Mm,
then as many slices as there are policies,
yeah.
because each policy is going to change how the world changes. Now, if all of these slices were the same, that would be like saying whichever policy you select, the world is going to change in the same way. So in that
Mm,
situation, there's no real causal efficacy or agency of that agent.
yes.
So B is really where it's at.
Mm,
And in this example, the B is just given and fixed. But there are other examples that we could explore that you can look up where there's B matrix learning. So that's
mm,
learning the consequences of one's actions through taking different policies. So that's a situation kind of like a multi-armed bandit, where you actually have to
mm,
learn the mapping between different things. Preferences here, C2 is the context associated preference vector. So we have if there's the dashed line is neutral. So these 3 elements correspond to these 3 elements: 0, 6, negative, and 6.
mm,
And then these 5 in the top C correspond to these 5. And then, as they say, there's a slight, they give a -1 to the starting position just to kind of bump it off and get it going. Because if it really had no preferences,
mm,
I mean, all of this comes into the parameterization. Why is it 6 and
mm,
not 9 and -9? Why not 9 and -2? That is
mm,
the parameterization question. So when we're in a pedagogical setting and we're just like
yeah.
looking to play around, that's when it's super helpful to have the code and like do parameter sweeps, or just by hand play around with how different variables change the outcome of the model. And then in chapter 9, it discusses more, well, how would you go from a bunch of videos of rats in the maze to inferring what the likeliest parameters are? But here they're just given. Also, just note that these values are given in a way that it's actually like e to the blank. So the 6 here has actually a very interpretable meaning in terms of the ratio of the preference. So this is not just like 6 arbitrary points, or like, I don't know. It is just literally describing kind of like the odds ratio.
Right.
D, in the context domain, it's just 1/2, 1/1. Or it could have just said 0.5, 0.5. but they're conveying that it has to sum to 1. Something must happen. This is a distribution, and the values are the same. So uniform distribution. This is a perfect knowledge over the starting position.
Right. Daniel, can I ask you a question here?
Mhm.
So this D2 is half and half probability, right?
Mhm.
But this is not known to the agent who makes the active inference, right?
It is known. It starts out completely unsure. It starts out with a 50-50 belief. But it's kind of funny because it's like it's 100% sure that it's 50-50. Like same as a coin flip. You're 100% sure that it's 50-50.
Mm.
If you had a more sophisticated model, and it is shown in a later figure, you could have
Mhm.
a hyper prior on
Right.
D. So you could ask, how
Mhm.
confident am I about the prior? You can do that for any of them.
Okay. Okay. So you have a hyper prior that can characterize D2, maybe characterized by some parameter, right? So you can later on learn those parameters. So you can-
Exactly. Exactly.
Okay.
Any parameter that you want to learn in a Bayesian statistic setting, you need a hyper prior. If you
Okay.
don't, if it's just a fixed parameter, then it's like the equivalent of the Dirac delta function. It's just like a spike. Like you have like it's just like a single observation.
Right.
Yeah. And it's always a very interesting thing in this case, or in your own generative models, like what is being made explicit and then what is actually being kept implicit. For example, like how does the rat know that it's going to get the information at that location?
Right. More question. How does the rat know it's half and half?
It's just given. It's just given. I mean,
me.
that's like asking how does the rat know that moving to the left is going to get it to the left? But also keep the figure 9.2 in mind. Weird, it's like you can't. (9.1). We're making a map of the rat. Here is literally figure 4.3 or figure 7.3 right there. D is not shown. So we're just describing its map of its space. We're not claiming to make a total account of everything that the rat knows. But yeah, I mean, there's more to say on this example. Then there's an I example. Here in 710, here's the prior on D. Here's the lowercase letters are hyper priors on everything. Then another example with a maze finding agent, and then a hierarchical nested model where you put a GM as a leaf in another GM. And that is shown in a nested example. So it's kind of a long chapter, actually. But because there's a lot of examples that are kind of like densely packed. But just in our last like minutes here, what does anyone find interesting, or what questions they still have?
Well, I still have one more question in the end of section 7.3.
Okay.
The so it's 2 sentences above 7.4.
Okay.
Yeah, you're still at
Okay.
okay. I think further up. So it talks about the neuronal activity. Okay, yeah. So the second to the last sentence, they talk about field potentials and neural activities, right? In figure 7.2.
Yeah.
So my question is, how realistic is this team-based model comparing to the experimental data? So we have this is a simulation, right? So basically we constructed the active inference model using the data to simulate the activities of a mouse in the teammates. So my question is, how does the simulation results compare to the actual biological experiment, the activities of the mouse and how their brain, the mouse brain activities, imply or corresponds to this numerical simulation?
I'm not aware of them doing this in a rat, doing the T-maze, but it may exist. We should look it up. In other settings, it maps very, very well. Now, that's just like, from my perspective, it's just a bonus because active inference is not developed as an account of brains. The particular partition, the Bayesian mechanics, all of the cognitive physics doesn't need to be about any specific system. However, as the empirical lines of work have shown, various features of the model that are very non-trivial are recapitulated in biometrics. That suggests that the analytical solution and the biological embodiments have a convergent strategy. An example of that is predictive coding. Predictive coding was invented by humans as a way to do video encoding because it turns out that frame differencing is the most efficient way to do video encoding. Like instead of just trying to compress every frame, you basically compress the B matrix, because if something doesn't change, you don't even need to mention it in the next slide. So predictive coding was a purely information theoretic consideration, but it turned out to be utilized in neural coding situations. So I see it as positive where it aligns, but where it doesn't align, then it doesn't. It just means that there's something else happening that isn't just narrowly that.
Yeah, because you see in figure 7.2, they show the neural activities and the firing rates and local field potentials. So there must be some mechanism to translate the outcome of the numerical simulation into those neural activities, right? The biological embodiment of the numerical results. So through what mechanism do they transform this numerical into the field potentials, for example, neural activities?
Yeah, it's all in the MATLAB code, in the MATLAB functions that are used. It describes it in more detail, but basically the LFPs are associated with belief updating.
How about firing rates? Are they associated with
yeah
decision?
I mean, you could imagine different different firing rates or different, I mean, and this has been studied extensively in the fMRI and EEG setting. You know, does the ERP in the ERG, or does the local field potential associate with a more intense stimuli, with a more expected stimuli, with a less expected stimuli, with learning? Those are all hypotheses that people have explored. And for different stimuli in different settings, you see different patterns. Okay, any last comments here?
I mean, I don't want to keep us too long, but I just, yeah, I still, as a last bit, I find the novelty seeking rather interesting. Like just the example, it's roughly around page 145, 146. Like if you were to model, give it, like if there were an absence of preferences for an agent, then like I'm just quoting here, the drive to novelty resolution given by expected free energy minimization leads our simulated creature to avoid any previously visited locations. Just like, you know, it becomes like a purely like the model is attempting to resolve expected free energy, if I understand this correctly, by just, it's just seeking more and more information. It's going to places it hasn't been before. There's nothing pragmatic about returning to previous places. It's not attempting to realize any preferences that say I need to go back, right? So I just thought that's a really nice kind of emergent property that we see whenever you leave out preferences here, and it for me it kind of lays a lot of emphasis on like the importance of preferences, their impact upon behavior in these models, and just maybe makes me think of like how to, you know, maybe start with preferences, how to model those appropriately, because it can highly impact right, like an agent's behavior.
Yep, great points. And the strength of the preferences overall, and where that ends up on a continuum between novelty seeking and basically ruthless pragmatism. Indeed. All right, thank you all. We go into chapter 8 next time in the later time slot. So peace till next time. Bye.
Thank you, Daniel. Good day.